So good afternoon, everyone. So now we are going ahead with our next session. So this session is basically on tutorial. So Dr. Andriy will be taking a tutorial. So as the topic you can see here, it is on structural determination by TEM and measurement methods of glass forming ability. Okay, so just take part. So you can discuss more on this. He will discuss few things on TEM and all. So whatever techniques and whatever thing he is going to discuss on tutorial, so just make an interactive session. Okay. So now I requesting Dr. Andy to start with his tutorial. Thank you.
Okay, let's start. So first I will start the first part, the structure determination by TM, and we will see if we will have enough time for this second topic. Otherwise, I will integrate it to the lecture. So first is structure determination by TM. TM, this is transmission electron microscopy. And as the famous physicist Richard Feynman said in 1959, that it would be very easy to make an analysis of any complicated chemical substances. All one would have to would be to look at it and see where the atoms are. So there is plenty of room at the bottom. In our lecture, morning lecture, we know about the crystalline phases. And we, for example, we want to know about the structure, about the defects in these materials. So for that, they need methods of structural analysis. There are different methods like X-ray diffraction, which give you information from larger volume. In the case of TM, this is direct method of structural analysis. So you can see direct space in the X-ray, XRD, you see mostly reciprocal space. In TM, of course, there are different modes of TM, and then you can see also direct space by using electron diffraction. And so in my lecture, in this tutorial, I will consider why do we need transmission electron microscopy. So what are the limitations of TM? Then I will show you some main components and defects of the TM. And I'll consider also a large topic on specimen preparation. And then I will show you some analysis in the TM and some examples. So first, why do we need TM? Why do we need transmission electron microscopy? So TM we need because, as I said, it's a direct method. We can see the structure in the direct space. And so if you want to resolve atoms, we need tools allowing to resolve such small objects. First of all, let us look some criteria to how to resolve the objects between if you have two points, and what are criteria to resolve them. This criteria is like given by Rayleigh criterion, and he stated that you can resolve two closed-spaced object by this equation. So it's equal to the 1.22 lambda divided by n sinus alpha. Lambda, this is wavelength. In this case, this is the light, and this is numerical aperture, and alpha, this is diffracted angle. So we can consider different cases. One is the unresolved case. So if you have two objects which are closely spaced to each other, then and if our system does not allow us to resolve this between this object, we will get one point, one intensity. This is the limit, Rayleigh criterion limit, which allows to resolve close-spaced objects, and this is in this case we are talking about the resolved objects. So as we can see here in this equation, we have this is lambda. This is wavelength. In this case, this is wavelength of light. Here with light, with optical microscopy, we are limited because of the wavelength of light. And if we can decrease the wavelength of our radiation, we can get here, as you can see, this is just a first approximation, just to get an idea. We can increase the resolution of our system. So let's look to the sources. If we use UV source, it has the wavelength like 400 nanometers. Then we can theoretically resolve objects like 200 nanometers. If we use soft rays or hard rays, X-rays, so here we have the wavelength of 7 up to 0.7 nanometer. Then we have can resolve the objects like 9 and 3 nanometers. And in the case if we use electrons, the wavelength can be different. But in the case if we use this electron energy of 300 kilovolt, we have the wavelength of 0.00197 nanometer. And so this is so we can resolve the objects or spacing which are less than 0.1 nanometer. And just like for you remember that atomic diameter in our crystal lattices, this is dependent on the type of atom, but this is in the range of 0.6, 5.2 angstrom. So by using this wavelength, we can resolve the atom in our crystal lattice. Based on this, on electrons, the TEMs are constructed. So they used electron beam instead of light. And if you look to the resolution of TEM system, it's like this is the graph showing you resolution, and this is the year. So the first microscope, they're limited by resolution, by the lenses, by the defects we will consider today. And then after here was little bit improvement with resolution. And then at this year, Harald Rose, they introduced aberration corrected. And so if the first TMs, they had resolution like 10 nanometer, it was also nice to resolve some biological objects to see them directly. The new era of microscope, they allowed the resolution 0.5 angstrom. So you can see here atomic diameter between 0.6 and the resolution 0.5. So this is the image of typical TMs, different TMs. So this is TECNI with 300 kilo electron volts. This is this microscope. Actually, this is a high vacuum system, and behind this is high voltage tank. This is the high-end microscope which I operate in Leipzig. Here we can reach this resolution like 60 picometer. This is IRM built in Japan. Here they have the voltages like 1,300 kilovolt. So you see this is the high voltage tank, very huge. And this is the microscope itself. It's very small. And this is the operator. And this is just, these microscopes are very expensive. So we are talking here about these like between maybe 3 and 6 millions, depends on the options you have. But you can build your own microscope just for fun using Lego. And the most modern microscopes, they have special resolution between 0.2 nanometers like that, and going down up to until 50 picometers like this or this. But the price, as I said, it's in the order of several millions, depending on the option. So what we can do with a microscope, we can study, we can see objects which cannot be not seen by naked eyes, or light microscopes, or even ECM. So this is one example. This is the solar cell, typical solar cell with 15 by 15 centimeters. And this solar cell has some fault areas, fault spaces. Here you can see in the dark light, if a thermal image here, So they appear as like hotspots here, like large hotspots. And if you want to study this and want to find the reasons of that, so you need a facility to see here locally. So we did it, and we found here a high number of different dislocations forming at the grain boundary of silicon, grain boundary, or directly in the silicon. So we can see here defects in our materials, like dislocations, which cannot be seen by other methods. Also, we use TEM, transmission electron microscope, or microscopy, for structural and chemical analysis at atomic level in real space and in one setup. So this is example of antimony telluride. Here you can see the real structure direct. This is antimony. This is antimony rolls. This is tellurium. But from high image, you cannot distinguish between them because the atomic number of both columns pretty close. This is 51, 52. So, and you can see that it's difficult to distinguish. But if you do EDX, atomic resolution EDX, then you can nicely resolve the layers, like these blue layers, these are tellurium, and these red layers, these are antimony. And of course, we can use also TEM for quantitative analysis, like the spacing in the crystal lattice. Like if we want to study some maybe relaxation in the lattice, some strains, or some real features like distances between these so-called vacancy layers or van der Waals like gaps. So now let us look to the limitations of TEM. This is nice image, what we see here, but this is our all objects, what we see here. We see it's in 3D space, X, Y, and Z. But in TEM, as you can see, it's only 2D images. What brings this, the problem into of such such projections? So if you see this image, you can maybe recognize these are lips, like huge lips, which are magnified and put here. But this is again 2D projection. Yes, 2D projection. Now, if we look these objects from our projection, like rotated a little bit, maybe we see, maybe this is still some lips, maybe the mouth a little bit open. But now, if we look at from another projection, we can see this is a sofa. So just it's I took it in the Deutsches Museum in Munich, and this is really nice example that in TEM you have 2D projections of 3D objects, and this is fundamental limitation of TEM. So you should think about this and care about this. Of course, another problem with TEM, these are electron beam damages. You have a high energetic beam which interacts with your specimen, and what can happen if you bring so much energy to the small volume, you can destroy your specimen and your structure. This is one example of TEM image, and this is what it was, glass containing some nanoparticles, and this is after 20 seconds of illumination in TEM. So the structure transformed completely to the amorphous structure. So you destroyed your initial structure. You also should think about this, and if you know this issue, this problem, you can maybe play somehow with your settings in TEM. You have different settings. You can adjust beam energy. You can adjust beam dose, and you can maybe use such like special methods like low dose for image such very high sensitive materials. Also, one limitation. This is the TEM specimen preparation itself, because for TEM work, we need the specimens which are very thin, so they should be thin less than 100 nanometer. And I speak about this projection, so they should be like in this. Like if your beam go to your specimen, this specimen should be less than 100 nanometer. Otherwise, if it's thicker, you first it impacts the resolution of your image, like shown here. This is 60 nanometers. Here, if you want to study interface, it's really blurred. And if you go down with the thickness in this projection, like if you can go down, can reduce the thickness, you can get better image resolution, like here for 20 nanometers. Then you can see nicely resolve the interface and to see some atoms coming from the interface into your thin films. So for conventional work, you need like samples like 100 nanometers, and for very high resolution work, you need specimens which are in this range between 10 and 30 nanometers. So now let me consider some main components and defects of TEM. So let's look and compare what we need. So first I will start with light microscope. Maybe you have used already during your work some there. So the light microscope, it needs a source that uses light source. Then it needs some lenses, glass lenses. And then it needs the ocular. So there you can observe your image. If you want to construct a TEM, this is the main components, let's say, the same. The basic idea is also the same, but you need a vacuum system. So you need to bring your microscope into a vacuum system. Why? Because you need electron beam. You use, instead of light, use electron beam, and electron beam you can get only in vacuum. So you need a vacuum system. Then to manipulate with electron beam, you need special lenses, and these are electromagnetic lenses instead of simple glass lenses. Then you need a very thin specimen object. Here you can use bulk material, and you need objective lens, several other lens, like first the image here formed and projector lens, and then final image you need a fluorescence screen, and then you need maybe some CCD cameras to observe your image, to record it. Here maybe you need also some CCD cameras or TV cameras to record your final image. And here in TEM, in the case of TEM, you need a vacuum on the average 10 to the 5, 10 to the 6 Pascal. So it's a very high vacuum system. Here, let's look more closely to the system, to our electron microscope. So here we have electron source. Then we have a gun lenses to focus your electron beam here, then to accelerate it, and then the beam goes to the condenser lens. There, it's transformed further to the objective lens, which is a main part of a very important lens in the TEM. Then the electron beam focused can be made here by condenser lens system, either parallel or focused. Then then the system brings to the specimen, and then it goes further. Here you have some apertures like objective aperture, then selected area aperture for selected area electron diffraction lens, projector lens, and screen. They observe your image. So actually, four main parts. This is the illumination system, which comprises electron gun condenser lens system that focuses electron onto TEM specimen, then specimen stage, which allows specimen to either be held stationary or else intentionally moved, or imaging system contains several lenses that together produce a magnified image, and acquisition system like CCD cameras, detectors, or spectrometers. So now to the electron guns. So So first you need to produce an electron beam, and there are different types of electron sources. There are like two types of sources, like fermonic electron sources and field emission electron sources. The fermonic electron sources, they are made either of tungsten or lanthanum hexaboride. Here, tungsten, you see, it's made of like V-shaped filament. Here, LAB6, lanthanum hexaboride. This is short rod and sharpened to tip. So actually, it's adjusted to this filament. Here, this is the LAB6 cathode. And for field emission gun, we use either tungsten or tungsten covered by zirconium dioxide. And here, the source is very sharp here. It's very sharpened. And they use both different physical effects to extract the electron. Here, you are mainly just heat up your sources, and then you can get electron beam in the vacuum. Here, this is in the case of field emission electron sources, you use either cold field emission or thermal assisted emission, Schottky emission effect. Because here the source is very small, on the average very sharp. You can extract here the electrons by this field emission. So why do we need different sources? As you can see here, that the large diameter of our sources here, and this is the small diameter of our sources, and here it affects the resolution of our system, and because this is the first pass of our TEM, and so here we have the resolution on the average. Maybe you can reach here 0.2 nanometers, here like 1 or 2 nanometers, and here this depending on the system, of course, lens system, and here in this case you can get a much better resolution compared to these sources. Actually, this type of sources are also used for scanning electron microscope, not only in the TEM area, but also for scanning electron microscope. Mainly used this, but also many microscopes are also equipped by this FEG because of better resolution. So now let us look to the electromagnetic lenses, how they are constructed. So electromagnetic lenses like condenser, objective, diffraction, intermediate, and projection. These are electromagnetic lenses. The gun lenses here, they're electrostatic lenses. So the electromagnetic lenses, how to make them. So electromagnetic lenses, they mainly consist of two parts from a cylindrical symmetrical core of the soft magnetic material, such as soft iron yoke, and second, a coil of copper wire which surrounds each pole piece. So this is the cross section of such a round electromagnetic lens. So this is the yoke. This is the first part, and inside of this yoke, like we have copper wires which are rounded and so seated here. Now to make the magnetic field here more stronger, we need some pole pieces inside the lens, which make the distribution of magnetic field here more uniformly. So this is the image of such a lens. This is really a round magnetic lens. It's like here, this is the yoke here, and copper wires are inside. And because we need to apply it here high current, we need also to somehow to cool down this magnetic lenses, because they otherwise you have so much heat which can influence also your field and your work. So now let us look the function of these pole pieces. Why do we need these pole pieces inside of the lens? Like here, they can be as a part of the lens, or they can be constructed from two lenses, one lens, another lens, and you have also the pole pieces in between. So here, this is the cross section of such pole pieces. One is that these pole pieces, they strengthen your magnetic field here, and here you know that the electrons in the magnetic fields, they are deflected, and they make like circle rotation in this case goes like rotated in the field. And if they make analogy to the optical lens, these pole pieces, they act like a small glass lenses. So they use like a focus, like for focusing or defocusing. So they bring your electrons from one point to another point. So the magnetic field pole pieces act as a thin lens in optical term. And because these are electrons, you can better manipulate them by using electromagnetic lenses. And in this case also, because we made always analogy to the normal lenses, we can also apply elementary lace equation to these short magnetic coils. So this is some images inside of the TM. As I said, the pole pieces can be as a part of one lens inside of the lens, or it can consist of two parts. Like this is one part of the lens, this is the second part, and these are pole pieces. This is objective lens. This is a third of each TM. So inside you insert your specimen, which goes from the side. And the magnetic field which you create here, it can reach the values like up to 2 Tesla. And this is very important to know, because if you use your magnetic sample and if you don't care about it, sometimes you can insert a large magnetic sample like the size of 3 millimeter, and then this sample can go out of your holder and stick to the pole piece. And then to get it out, you need to open your system, which is also not good to the vacuum, because you have to be careful not to scratch the pole pieces. Otherwise, you will get non-uniform magnetic field. So now let us look to the defects of the lens. They are not perfect. So, and then they have defects. They called like aberrations that affect their performance. The resolution of electron microscope, we can just approximate, is defined on very simple case. It depends on the wavelength of the electrons, and it's also a function of CS. And CS, this is the aberration coefficient. And so you can see, if you make it smaller, this value, we can get the nice resolution. So we can how to manage this and to adjust this. So there are different type of aberrations in electron microscope. One is this on-axis aberration. This is spherical and chromatic aberrations. And off-axis aberrations, this is coma and astigmatism. And there are also distortions. The off-axis aberrations, we can adjust it inside of the microscope. But these on-axis aberrations, spherical and chromatic aberrations, you can adjust on high-end microscope if you have a spherical aberration corrector. But on standard microscope, this is like a fixed value, which fixed values which are not adjustable. Let us look to the effect of this CS value on the imaging. So this is maybe you know about the Hubble Space Telescope, which allows us to observe different galaxies. And as it was constructed, here the first image of the galaxy, like M100, they looked and found, oh yes, we can see it, but this image was blurred, and this was because of aberrations or defects of the lenses. And after correction of this aberration, the image of this galaxy it appears much more clear. You can see some details which cannot be seen here in this image. And that was really big project because you have to go in space to replace the lenses, and then everything should go right. And if not, then you have some troubles. But at that time, they could manage this problem and insert a aberration corrector, like different beta lenses with low CS value, and to see to get better image. So how to correct this aberration? Again, we can look to the optical system, and first we define what is spherical aberration. Spherical aberration, this is inability of a lens to focus in excident beams from a point source to a point. So if we have a non-ideal lens, and this is incoming light to the lens, then we will have many focal points, which brings you that your image is blurred. Then if you get ideal lens, then we can bring all the lights coming from the lens, diffracted lights, to one focal point, and then we can see a clear image. So how the correction is done in the case of glass lenses? In the cases of optical microscopes, you have a convergent lens, and then if you insert divergent lens, then you can correct this problem with many focal points. So the focal points, if you look this array path diagram, they make your image like larger and blue, which brings this point P to the point P to the larger point. So, and P prime, would say here, P prime, it will be much larger, and it goes like point spread disk here. And if you insert a divergent lens and which correct this, which brings all lights to lines to the point, then we get P, our point of interest, also focus to the next point prime, and this so this brings this we get better and clear image. But so now the chromatic aberration, again to the glass lenses. So chromatic aberration, this is a lens focuses each of those colors at a different point, causing a finger color to appear around bright objects seen through the lens. This is problem called as aberration correction. So here we have incoming light, and you know that our light consists of different wavelength, and here colors in simple case. And so if the chromatic aberration, this is inability again to focus all these colors to one point, and this also brings to the problem of blurred image. And if you don't have the chromatic aberration, then our image like appears like this hole, like a hole here. The problem with electron sources that they have a special, they have energy spread like 1 eV, and or sometimes more, sometimes less. But this brings also to the problem of chromatic aberration. So now how to compensate it in the case of glass lens. So again, we have here our lens, incoming light, which cannot focus all the beam. So and if you put another lens in between, like concave lens, which can compensate these different paths here, then we can bring all lines to one point. But the problem in the TM that all these electromagnetic lenses, they are all focusing lenses, and it's difficult. It's difficult to make like divergent lenses, like in this case. So we need a special part, special lens in the system, like it calls corrector. Here in this case, you see this is corrector, which have additional coils, and by these different coils, if you can calculate aberration of your system, of your beam, then you can adjust this and correct the CS. So what does it bring to the imaging? It was shown in 2003. So this is the latest image of strontium titanate. It consists of this projected images in 110 projection. It consists of atomic columns of strontium oxygen here and titanium oxygen. If we have high spherical aberration of the system on normal microscope, like 1.3 millimeter, you maybe can resolve some here atomic columns which belongs to strontium and oxygen. Then you change adjust the CS, reduce it to 30 micrometers. Then you can see more features in the image, but it's not the same like this. And if you adjust the CS to the minus 40 micrometers, then you can see, can you nicely resolve the atomic columns, which corresponds to the real structure. And the high-end microscope, they all contains similar correctors realized by different manufacturer. Maybe they can have little bit different design. So now to the recording media. After we create the image from the specimen, and after we can see it on the screen, we need to record it. In the case of TM, we use a CCD cameras. In the case of the scanning transmission electron microscopy, we need different detectors like HADF detectors, ADF, and bright field detectors. Also to collect some signal, to get some chemical information from your specimen, you need some EDX detectors which are located above the specimen, and there is also another detectors for chemical analysis. This is like electron energy loss spectroscopy detector, which is situated underneath of the specimen and the all lenses. So this is some images of a camera, of image acquisition. So this is conventional plate camera. It has been used for several years and decades after invention of the microscopy, and then after development of CCD cameras. Now the new microscope are equipped with this, with digital imaging. Here you can also make the digital image after scanning, but still old microscope, they used this system plate cameras. As I said, the newest microscope, this is used the CCD cameras. The price, of course, the difference between these both, and before it was also some troubles with the sensitivity of CCD cameras. The plate cameras, they were more sensitive, but now we have a huge development in this direction, and there are also direct CCD cameras which can directly count the electrons. So some comparison advantages and disadvantages of recording media. Of course, the negatives, advantages, if they have better dynamical range, better signals to noise ratio, larger field of view, low dose application. The advantages of CCDs, fast acquisition and result, online mediate measurements analysis, cheaper for long term, and better vacuum. But inconveniences that no immediate image available, darkroom photographic processing, negatives mounted on thin film frames, and you have to pre-pump your plates, and then you have to exchange it. So here, some inconveniences is small field of view and low signal to noise ratio, but as I said, they improved over the years, but some old CCD cameras, they still have these problems. Now, if you want to use a scanning transmission electron microscopy, then they use detectors instead of CCD cameras, and there are different types of detectors situated underneath of the specimen. And here the intensity which comes from the specimen, they are recorded pixel by pixel by such detectors. They can also record different type of signals from your specimen, and so there are some backscattered electron detectors which are located above the specimen, but there are not so many systems which have this. But you can use it, and the signal will be pretty maybe the same as in the case of scanning electron microscope. Now, a few words about specimen preparation. So some maybe requirements for TEM. So first, in TEM, because of the design, we saw that there are not so much space inside of the microscope. We also need very small specimen. This is like here, the specimen holder, and the specimen itself, it's adjusted here to the 3 millimeter. This is 3 millimeter diameter. There are special specimen grids to adjust your specimen here, made of different materials. And so as you can see, if you have your bulk sample like 10 by 10 millimeter, you have to transfer somehow this to your grid. But because it has a thickness also like more than 100 nanometer, you need first to prepare it before to transfer to a specimen grids, and then to the specimen holder. That is why we need the specimen preparation. Also some words to requirements also to TEM work. So your specimen and your specimen holder should be as clean as possible. The problem is that you have a high vacuum system, and it's not a good idea to bring some dirties to the system, because you cannot easily clean it by yourself. You need to have a manufacturer. So that is why before each work you use plasma cleaning. What is a plasma cleaning? Plasma cleaning. This is it helps you to clean and remove some carbon contaminations from your specimen in a special plasma cleaners. So if you have a plasma consisting, for example, from argon or argon and oxygen, or hydrogen and oxygen, then it can bounce some carbon complex from your specimen from the surface, and it can go to the plasma cleaner, and so you can then you can remove this some H2O and CO2 complexes from the specimen holder and from the specimen itself. So here, this is one example. How does it work? So this is the image, and this is the carbon contaminations on the surface of this image. And if you make a plasma cleaning for several minutes, like 1 minute, this is for after 1 minute, and for 4 minutes, you'd have to adjust your time depending on these contaminations, on the thickness of such contaminations. Then you can remove them from the surface of your specimen. Sometimes you can also see the formation of contaminations on your TEM specimen, because you have some residual gases in the TEM, and they can also, because of electron beam and surface gas interactions, you can produce some like contaminations on your specimen surface, and by using plasma cleaning, you can effectively remove it. So now let us look to some scattering processes in the TEM. Why do we need very thin specimens? So if you look to the scattering process, and if you consider bulk specimens, which you use, for example, for optical microscopy or scanning electron microscopy, then you can have different scattering process, like incoherent elastic scattering here, formation of secondary electrons or incoherent images. But because your sample is very thick, then you have here so many multiply scattering in this sample that the electrons cannot go outside of the specimen. So what do you need? You need to reduce the specimen thickness here up to several hundred of nanometers, like let's say 100 nanometers for high voltage microscopes, like 1 MeV. Maybe you need 500 nanometers, but for typical microscope that they use, they have electron beam energy between 200, 300, sometimes 800. You need to reduce the thickness of your specimen below 100 nanometer. And if you can do it, then you can also have a beam which can go through your thin specimen, and then you can get different signals, like coherent elastic scattered electrons, incoherent elastic scattered, incoherent elastic forward scattered electron, and also direct beam. And these all electrons which are scattered by different processes, you can use to analyze your sample. So now specimen requirements, like just a small summary, short summary on that. So due to strong interaction between electrons and your solid, the specimen must be very thin, less than 100 nanometer for TEM work, and less than 30 nanometers for high resolution and spectroscopy. The surface of your specimen should be clean and free of artifacts like contamination. Preparations should not affect microstructure, like mechanical and chemical. They should unchanged. And the specimen for TEM observation must be representative of the true nature and morphology of the material. But of course, it will be impossible to prepare a specimen without any artifact. So we need to know a method and the artifacts which we produce by a special method. And if you know this, we can somehow overcome this all problems, or we can just distinguish between the artifacts and real structure. So now let us look some real specimens. What do we need and how it should look like? Let us consider the nanoparticles which transferred on the carbon support, amorphous carbon, and here we have different situations. One is the vacuum. Here you see nothing. Here then you see here one area. This is another area, and this is the third area. So this area belongs to the amorphous carbon. You see here this is disordered area. No ordering in this. So it comes from the TEM support. Then we see here our ideal specimen. So we know this is the support, and this is the vacuum, and this is our specimen. So this is nice. It has very nice contrast. You can distinguish between atomic columns. Maybe you have some amorphous layer on top, but it's not too much. It's pretty nice area. But if you combine this pretty nice ideal specimen with amorphous carbon, this is usual situation in your work, then you can recognize that the intensities of the atomic columns, they are changed here. You have dark regions, you have more darker regions. So maybe you can think about you have here defects, but it's not, because here you have like a superposition of your ideal specimen and amorphous carbon, and this is influence your wave, electron wave, which goes out of this specimen. So in ideal case, you have to prepare the specimen which looks like this. So now there are different types of specimen preparation. So they are listed here. Of course, I will not go through this all of these, but there are like 6 groups. Like one is based on ion thinning, and now there is this mechanical TEM specimen preparation. Third, this is chemical and electrolytic specimen thinning. Fourth, this is preparation techniques for dispersed or ultrafine material. This is replica preparation, very old technique. And this is contrast enhancement and labeling preparation. These are more for the biological specimens. So today I will consider only these both ion beam myelin and focused ion beam thinning, because these are common methods now in the science and the research and also in the industry. They're based on this ion beam myelin. So the standard, or more common now, more famous, this is focused ion beam thinning, or FIB. So let's look first to the idea how it's work. So this is the ion beam myelin. It's commonly used method in material science, and here it's based on the use of ion beam myelin of your specimen. It's use like ion beam source and special ion beam system. Here the goal is the crystalline lattice destruction at the surface, followed by ejection of superficial atoms. So here you just like amorphize your surface, and this then will be etched away by ion beam. Here you can prepare cross-sectional and plane view. Here we can consider some processes of ion-solid interaction. So if we bring like ion onto the surface, we can get also different events here. Like we can have sputtered electrons, a particle like ion or neutral. We have also here some secondary electron emission. We can have also implanted ion, and we can also produce some surface damaging. And this is pattern. This is the base idea, that we can sputter the material from the surface. First, we amorphize the surface, and then this amorphized layer will be sputtered away. So for normal cross-sectional preparation, there are different steps. like if you have a thin film attached to the substrate, first you have to reduce the size of your object of your sample, like you have to cut it onto pieces, then you have to glue it together, then you slice your block into smaller blocks, then you take these small blocks and then you reduce the thickness like from 0.5 millimeter until to 0.8 millimeter. It depends on your skills. And then afterwards you make like make dimple. You go to the dimpling system and then like here take away mechanically some materials, and so you get here the thickness of the area in this after dimpling like can reduce up to 0.2 or even less. Again, it depends on your skills. And then you go to ion milling and then you process your specimen. So this is after dimpling. Your specimen looks like this. You have here reduced thickness after dimpling because it's like a wheel, and then to stabilize the overall system, there is these parts. The edges are more thicker than inside. And then by using ion beam from both sides or from one side, you just remove the material from top and from the bottom. So I think we can continue further after the break. These 5 minutes we can use for the questions, if any. Just please ask me. Yeah, please. Just take this microphone.
Sir, so for my sample preparation for TEM, like the process was like just scoop it and then they did the ultrasonication and then do the plasma etching and things like that. But I think it didn't give a lot of. I think the sample preparation was not that great. So if we go to the FIB, like because we are using some argon or something, so is there any chance that it can react with the material and it can actually have impact on the material through the FIB mode of preparation, simple preparation?
Yes. But I will consider in the next part of my presentation. Okay. So I will consider some artifacts, how FIB can modify your structure, what artifacts are, and whatever. So of course, ion beam. I will also go further and show you some artifacts produced by ion beams.
So apart from FIB, which method would be the best simple preparation, especially when we consider chalcogenide materials, especially like GST kind of material?
Yeah, for GST it works very well, this ion beam preparation. If not, there is another so-called mechanical specimen preparation, and here like tripod polishing, it's solely based on the mechanical thinning. So you use special tripod and you make your specimen very thin just by simply making mechanical thinning.
Like that dimpling and all you're showing?
No, in this case you don't use the dimple.
Okay.
Here. You just adjust, you have like tripods, and then on one side you just adjust, then during the mechanical thinning, you adjust the height of these tripods, okay. And then you reduce, this is like wedge sample, and you make it, you polish it, and then you get on the edge very thin area. But there are also some troubles with issues with mechanical specimen preparation. Sometimes it can be mechanically unstable, the material safe, or you can make during this mechanical polishing, you can bring some stresses into the system or damage even the system. Of course, you can also use, this is also very nice method, ultramicrotomy. So here you use a diamond knife to cut your specimen like if you can just image you have your cheese and then you slice it by knife. It's also used. This is the main basics of my ultra microtomy, but this is very expensive. The knife is very expensive, like 1,000 euros, and then you need some just to learn how to do it, and it's time consuming. So for chalcogenites, FIB or ion beam myelin, it's one of the best choice to prepare the sample. Yeah. So, okay, let us make a break. 15 minutes. Yeah?
Yeah, we'll come back. Huh? Just take a short break of 15 minutes, then we'll come back again. Yeah.
Now we can continue our tutorial on TEM. So here there are some troubles with mechanical thinning, mechanical polishing. So what can happen? It depends on your material, if it's hard or soft. And if you use the mechanical polishing, you use a special paper which covered by diamond, or used paste with the diamond. The size is like several micrometers with grains of several micrometers or less of 1.5 micrometers. And what can happen? For example, in the case of aluminum, it can brings this diamond grains into your aluminum. Aluminum is soft, and so you can change the microstructure and structure of your material by such inclusions which you don't want to have. Then the problem is also with ion beam thinning. This is the surface roughening. This is because it's a method which you used based on this ion beam. So you have to amorphize and then remove these amorphous layers from the surface, and this brings some roughness. It depends on the on different parameters like energy of your ion beam, also the angle what you use, also the material itself, if it's flat or if it was before also had some roughness. So this image shows you the surface topography of sapphire. Here, after using ion beam milling for 30 hours and 1 kV, we get like roughness. So if you start with first the surface after cleaning with 4 or thinning with 4 kV and beam energy, this is the degree of the beam to the surface and beam current. And after, for example, 4 hours, you have the roughness of the surface 80 nanometers. And then to get it more smoother, you need to invest a little bit more time, but then you use less ion beam energy. And if you use less ion beam energy, you have to increase the time for ion beam polishing. So this is the graph showing the surface profile. This was ion beam mild with 4 kV, and this was ion beam mild at 1 kV. Sapphire, this is also very hard surface, and it's not so easy to prepare it. So you should know about it, and you have to adjust your ion beam milling parameters to your system. So another problem is also the thickness and the formation of amorphous layer. So here, this is the thickness problem, that your sample first is very thick, so you used ion milling with beam energy more than 2 kV, and then you see here the blurred image. And then if you use the ion beam milling at very low energy, like 100 electron volt, then you can polish the surface of your specimen, and then you can reduce the thickness and then get better resolution. So you see here some defects at the interface, and you see clearly the lattice of your thin film. Now the preparation of plain view specimens, so that it has also based also on ion beam, and this is pretty the same as before. as for cross-section here, instead of using like to slice like blocks and to cut your specimen into pieces or several pieces, you're interested in this surface, and what you need, you cut your block by a special machine. Here, this is like a block. Here, there's your thin film and your substrate. This is diameter of 3 millimeter because it's given by your by the size of specimen holder where your specimen will be inserted. So then afterwards you polished your substrate, your system from the substrate side. So because you're interested in thin film, so you go down the thickness of the substrate by using mechanical thinning, and then you use again dimpler, and you dimple your here from the substrate side to get to the thin film, and then you use the ion beam myelin as in previous case. So there are also some problems which are the same as in the cross-sectional myelin. So more on the artifacts which can be induced by ion beam myelin. So first we know about the surface roughening. So before ion beam, if your surface is flat, you induce some roughness to the surface after the sputtering. Then if you have a multi-phase system, then you might have this professional sputtering. So different materials, they have different properties, mechanical properties, toughness, whatever, and then hardness, and then some softer materials will be sputtered much faster away than the harder materials. So you should be aware of this problem. Then, of course, you can have alternation and phase separation on surface. Then damage formation by ion beam. As I said, it's based on the creation of a amorphous layer and then removing of this amorphous layer. And after the specimen preparation, you have always a thin amorphous layer on top of your specimen. It depends, of course, on the ion beam you used and also on the type of the specimen. Then ion beam also can induce intermixing into your system because during ion beam myelin you heat up a little bit your system, and if you have highly diffuse system, you can introduce the intermixing between two solids. So now, if you have such a problems, you can, of course, somehow to deal with them. You will try to find the solution. If you have the surface roughening on microscopic or microscopic scale, how to overcome this or deal with this, you just use the rotation of sample and small incident angle of ion beam. So you should rotate your sample at the sample, or you can rotate your beam, or you can use the small angle. Then reversional sputtering of inhomogeneous samples. Here again, you might use oscillating sample movement and use it on only one ion gun, so only from one side. So for alternation and separation problem of sample surface, again, you can use a small incident angle of ion beam and low accelerating voltage. And sometimes liquid nitrogen cooling can help a lot. Surface damage, like formation of vacancies, amorphous layer, sample bending, recrystallization, stress formation near the surface. This can be all induced by ion beam. Here, what you can use dual ion beam myelin on both sample sides, small accident angle, low accelerating voltage, and again, liquid nitrogen cooling. So now let me go to the focused ion beam thinning. This is very famous method used nowadays. but it's very expensive method. It's not like ion beam system. For ion beam myelin you need Dimpler, also some stuff like diamond paste and diamond saw system, and for FIP ion beam focused ion beam myelin you need a special systems. They're called focused ion beam. So this is actually, it looks like a usual ordinary scanning electron microscope. This is FIB system from the FEI. This is from the size, and the difference to the normal space to the normal SEM, instead of two columns, one column you have two columns. Also, as in the case of ACM, you can adjust different options to your FIB system detectors like EDX detector and whatever. You can use it. The system very flexible, not only for TM specimen preparation, but also for maybe surface structure and also for cutting of your specimen and looking the cross section without to go into TM. However, such systems, they are very expensive, and the FIB may cost between 30 and 80% of the total cost of the TM. So the price can be also on the average on 1 million, 1 to 2 million, depending again on the options. So now let us look more closer to the focused ion beam system. As I said before, it's based on the SEM. So in the FIB system, you have SEM column and FIB column. You have a manipulator and gas injection system. You can also use the system without FIB, but it's not so very convenient if you want to image your sample, adjust the sample for the preparation and then image after the preparation. But the first system, old system, they have only one FIB column. Why? Because the FIB, the focused ion beam, you can do three things, like different operation modes. One, if you use low ion current mode, then you can make FIB imaging, but because the size of ion beam is very larger than of as an ECM, your image will be, the resolution will be not so good. Then if you increase the ion current, then you can remove your material from the surface away. And you can also use ion beam assisted deposition by using ion beam and this gas injection system. So these both you use, these three modes you use in your system, in the FIB system, but primarily and this main mode which you used for the specimen. This is for the imaging, and this is for the preparation of protective layer. So the application of FIB, as I said before, it's used by semiconductor industry very often for failure analysis, for prototype circuit rewrite, and for mask repair. And one is also the TM specimen preparation for failure analysis. For research, you can use it for micro machining, for nano fabrication. If you use this mode, you can create some nanostructures, or you can grow nanostructures on your surface. And we are using it primarily for TM specimen preparation. So there are also different types of or methods of TM specimen preparation using FIB. The old one, this calls H-bar method. It's used in FIB without external manipulator. Then there is ex situ lift out, which used FIB without external used with external manipulator. It's wrong written. And this is in situ lift out. Here we use FIB with external manipulator. In this case, internal manipulator. So now let us look to the first method. This is H-bar method. for cross-sectional preparation, because we are still interested in the microstructure of our chalcogenide thin films. And here it's based as in conventional preparation method. First, you have to cut the slices from your specimen. Then you thin down it also up to, let's say, 0.5 millimeter. Then you attach this very thin slice to the half grid, here to a special half grid. And then you deposit platinum, like protective layer, on top of this, and then you can process the thinning in the FIB system. So how does it look like? So the specimen after this preparation. Here you have your specimen here, and you have two very thick edges from right and left. You can prepare such samples. You can also, a specimen, you can also refine it if you feel that your specimen is very thick. You can do further myelin, FIB myelin. But there are several issues or drawbacks that this method, that because you have here such thick edges like bars, then if you want to use X-ray analysis, they will be like shadowed, and your X-rays coming from the samples can be just here like rescattered, and then there is you will not get no X-rays, no X-ray or very low X-rays coming from the specimen. Again, another problem in such HR method, this is the redeposition from this thick area, so some materials can be redeposited on your specimen. However, it was like one of the first method introduced for cross-sectional preparation. Another method, this is so-called ex situ lift-out method. So you can proceed like with H-bar method, and then you, because of this problem with thick bars here and the problems of shadowing, and that you can get very low or almost no X-ray signal, then you want to transfer this your FIB lamella to the to another TEM grid, and then you use like external manipulator, so outside of the FIB in this case, and then you transfer it. The problem, so one you need like electrostatic glass needle, so you attach it and then transfer to the, here you can see it, this is the glass needle. It has very low contrast, but this is then it transferred. It attached like by electrostatic forces here between the lamella and the glasses, and then you transfer. The problem is here, one is with varying success rate, so you can lose your lamella on the way to the support. And in this case, if your FIB lamella is very thick, and you think I need to refine it, it's not possible in this case. So now to the in situ lift-out method. Here for this method, because you have internal manipulator, and you can use it for transfer of your FIB lamella like this to the special grids. This is called FIB grids. Then they have different boards here. They can make of different material, of molybdenum, copper, depending on the composition of sample. If you want to make like EDX analysis of sample which contains copper, maybe you want to take molybdenum grid instead of copper grid. Also, because you have different ports, you can adjust your FIB lamella on different sides, and then so you can have many lamellas on grid, and this will save your time for adjusting your specimen to the microscope. So for the work, you need to transfer your half grid to the specimen holder and then to insert to the microscope. It always takes a time for one sample, but if you have here multiplied samples, you insert it and then you can work the whole day or till 2 days. So, but the typical thickness of such half grids, this is like between 25 and 30 micrometers. So they are very delicate, so you can bend them very easily. It's in the case of copper, so be careful with that. Molybdenum, they are more stable. So why it's so interesting and important, this FIB method? Because first you can prepare the lamellas from a wide range of materials, including semiconductors, metals, ceramics, polymers, biological materials, and tissues. Here use cryofib. So the main advantage is the precise selection of the lamella position and preparation of heterogeneous samples with difficult material combinations like multi-layers. Here, this is one example. If you have like a device with the sizes of 250 micrometer, if you want to use conventional specimen preparation based on ion beam myelin, then you cannot get this. It will be very difficult to get this feature into a TEM specimen because you don't know where you cut. In FIB, because you can image your area, you can select it, and then you can cut precisely this. So this was like a device, PCM device. Then we could cut it. You can see here device, 2 electrodes, size 250 nanometers. Very nice. So this is another example of very hard materials. So during production of silicon solar cells, the silicon, the carbide and nitride can go outside of the crucible, and some precipitates can form inside of the grain boundaries, which impact the performance of such solar cells, can impact the performance. And in our project, we were interested in these features. What is it, and if they are silicon carbide or silicon nitride. Then they used FIB and prepared them. So silicon nitride, it's very hard material, and silicon, it's much softer compared with silicon carbide. But anyway, we could prepare the both filaments in this material and silicon in one. So in one lamella here using FIB. Sometimes you have here some problems already with deteriorations and defect formation, but many areas they will in touch. So this is also the advantage of such FIB system for preparing of so-called difficult materials which have different hardness. So how does it work? This preparation. So first you select your region of interest. Then you need to protect your region of interest by depositing of a protective layer. Platinum, it's widely used. You can use also another like carbon and tungsten, and depends on your system. But this is platinum. This is widely used. Then why do you need this protection? Because in the second step you need mile the trenches, and you mile the trenches, the ion beam comes from one side and from another side, and it can touch your region of interest and it can destroy it. I will show you some examples. To be sure that you cut your feature, your region of interest, sometimes you can set the marks nearby of your feature to be more precisely. Then after you make such trenches, then you have your internal manipulator. Then you attach your lamella. This is now lamella, thin lamella, the thickness of several hundred of micrometers. So you attach to the manipulator, and then you cut from the bottom and from the side here, from this side also. and then you transfer it to the to your grid, and then afterwards you proceed with ion beam milling from one side and to the another side. Here you can see already some troubles with FIB preparation, that if you make such trenches, your sample, it's like a wedge type. So here you can see that the thickness at the bottom is larger than at the top. So here this is much brighter, this is less brighter. So you cut it like a trench, so like in this direction. So at the bottom it's much thicker as here. Sometimes this is very good method, because it's a local method. If you prepare your sample, you prepare from small volume, and I showed you one trouble with TM. If you have a large sample, like 3 by 3 millimeter, and if it's magnetic, made of magnetic material, it was iron palladium, then if you do your work wrong, this material can touch to the pole piece. In the case of FIB, because you reduce the size and volume of your material, you will not have such a trouble. Maybe sometimes it can also jump some grains or something can jump from your sample, but not like you need to then to clean your pole piece. So another problem with FIB system, this is it can also can first introduce some intermixing between the materials, like it calls diffusion problem. So if you have silicon, aluminum, titanium system, aluminum can be like diffuse through the titanium, or can be redeposited. I think it's mainly like redeposition of your material on the silicon substrate, and they're very common problem in the case of FIB. In FIB, we use gallium. This is the common ion source. Nowadays, of course, you can read there are xenon sources, but in many labs you find this problem, this ion source, and one problem. This is the implantation of gallium into your material. So you should know about this problem, and somehow to think how to manage and how to overcome this. With other ion beam sources, you will get also, depending on the sample, also the same problems with ion beam implantation. And another also problem. This is the procedure and preparation of FIB of lamella itself, of such beam sensitive materials like phase change materials, chalcogenide phase change materials. So here we have like structure thin films. This is multi-layers of germanium telluride and antimony telluride. And if you deposit your protective layer, and if you do it in the wrong way, what you can do, you can induce the amorphization of your sample. So what we did wrong here in this case, if you deposit a protective layer, first you deposit the protective layer by using electron beam. It's much softer because the electron beam, it has low energy of incoming particles on the surface. It's very soft. You have to deposit it before the deposition of ion beam platinum. So if you deposit ion beam platinum, it can go directly into the surface of your phase change materials, and it can amorphize it. So as it was in this case, we were hurrying the preparation, and we thought, okay, we can overcome this step, because it takes also several minutes, like 10, 15 minutes, depending on your system. But as we recognized this problem, we said, okay, we need used electron beam platinum layer. Why we did not use it before? Because we used also protective layer. This is lanthanum aluminide to protect the surface of chalcogenide materials from the oxidation. And then we thought, okay, if we have such protective layer, then we don't need to use electron beam platinum. But the ion beam, because it has, if you make it with a high beam current, then the ions can come through this protective layer of lanthanum oxide, aluminum oxide. It was like 10 nanometers. Even for 10 nanometers, it goes through this protective layer, and then it amorphizes your structure. So we think on the ion beam interaction, it just to kick away the atoms in the lattice little bit, and then the system goes to amorphous. So you should also be aware of this and think, and please always use extra layers, like deposited directly in the system or externally. Here you see that the thickness of electron beam layer, this is like more than 200 nanometer, and even in these layers, the ion beam platinum can go to some extent into the E-beam layer. So just think about this, so that high energetic ion beam can destroy your structure. Another problem with ion beam myelin, as I mentioned before, that the ion beams they produce amorphous layer on your surface. So the problem, it calls like surface amorphization, and this deformation of surface layer, it depends on the ion beam angle, and it also depends on the ion beam energy used. In the FIB system, this angle is fixed, like 1 degree to 3 degree, because to reduce the damages of the surface. Of course, if you use the ion beam which are point to 90 degree to your sample, you can destroy it, like it's shown here. This is very nice example. If you go directly, then it's even at 1 degree you destroy it. But if you go with 90 degree here, then you will destroy completely your sample. So in FIB, you use angles, incident angle, like here 1 to 3 degree. And here we did also some simulations on the using the SRIM program to estimate how far these ions can go into your material, to the crystalline material. It shows the y-axis shows you the displacement number per ion, and this is the target depth. And if you use 30 keV, we can see that the ions can go to large distances, more than 16 nanometer. And in the case if we reduce the voltage, then we can go the ions can go up to maybe 5 nanometers. It can be also nicely supported by the experiment. If you use for gallium ion beam myelin, you use 30 kilovolts for cutting the wedges, and then you reduce your ion beam to 15, and then at the end to 5 kilo electron volt. Then here, according to the simulation, you should have like amorphous layer with thickness of 5 nanometer from one side, and on another side here, by using gallium beam with 2 kilo electron volt, we can confirm that this layer is like on the average of 5 nanometer, although the energy was less than 5 kilo electron volt. So there is some disturbances in the simulation, but you see this problem still exists on your sample. To the FIB, also to the preparation itself, some Some protocols they suggest to ion beam myelin from both sides by using like 30 kilo electron volts. Like for cutting, you use this is a maximum ion beam energy in your system. So you make your myelin from both sides using 30 kilovolt. But for the phase change materials, we found that it's too high, and we used for cutting only for this step for myelin of trenches 30, and then we go to the 15 kilovolt, and then use the ion beam myelin from both sides by using 15 kilovolt. And beam currents like on the average on 100 picoamps. And then at the end, we make a low energy ion beam polishing, like with 5 kilo electron volt and 2 gallium ion beam to reduce the size, the thickness of the amorphous layer. This is very critical for TM analysis, because in the case if you have 20 nanometers layer between on the surface of your sample, and your sample itself like 80 nanometer, then the thickness of your TM specimen overall thickness will be like more than 100 nanometers. So, and then it will be critical to do high resolution work. In the case if you reduce these layers, you see that the overall thickness of your sample then decreases, and also the of crystalline air also decreases. And then in this case, like 5 nanometers, it should be less than 5. It can be maybe not a big deal for your high resolution work. You can also reduce the size, the thickness of your specimen by using another argon ion beam system, so-called nanomill. Here you use also focused argon ion beam, but instead of using gallium, you used argon. Argon ions they are a little bit smaller than gallium. Gallium is much larger than argon, and here by using this you can process your sample specimen thorough. You can get better quality, surface quality, and the thickness of your specimen. So here again some stream simulation on the ion beam penetration into the sample. Here we use gallium nitride. Here we can see that if we can reduce the ion beam energy to 2 kilo electron volt, the penetration depth maybe it's up to 8 nanometer. Then if we reduce to around 0.8 kilo electron volt, it reduces to 4.5, and with 200 evolt, you can even reduce the like penetration depth into your specimen up to 1.5 nanometers. So here we also tested on our samples, on our specimen, TM specimen. First we prepared the specimen like by standard FIB approach, and then we used also low energy gallium ion beam polishing at the end, and then if we use argon ion beam polishing, then they can reduce the amorphous surface layers even to the low value, to the 3 nanometer. It was argon ion beam with 1.6 kilo electron volt, and if we even further reduce the ion beam energy of argon ion beam to the 200 electron volt, then we can get even better results. So can get with samples with very less amorphous layer. Here we also did some specimen thickness. Here this is the lamellar preparation of the FIB and some argon ion beam polishing. So the thickness was like on the average of 45 nanometers. And then after additional argon ion beam polishing, we could reduce the thickness up to 22 nanometers. And this is very ideal sample. You see very clear the structure, the atomic columns of silicon carbide and of gallium nitride. You can see also different phases of gallium nitride. So the low energy argon ion beam myelin, it's very helpful for specimen preparation. but for this you need additional system. They have focused argon ion beam and also like a secondary electron detector. They can see your lamella, and then they can focus your argon ion beam onto the lamella. So now, okay, it shows the principle how it works. It shifted, this it should be argon ion beam. It should be pointed to the lamella, so it's focused, and then by rastering other the sample, you can make your specimen very thin. And at the end, so I would like to show this image that the specimen preparation. This is also like a cooking. So for your material, for your system, you will try to find the best preparation method. As you have seen, there are huge number, but with FIB, if you know the limitations of FIB, if you know the limitations of your sample artifacts which you produced in your specimen sample, then you can prepare very nice, very thin specimen. It takes maybe time, 1-2 months, maybe 3 months, but then you can get very nice specimen, and then you will have a protocol where you can apply it to your particular system. Now there are several analyses in TEM which you can perform if you have very nice and thin TEM specimen. Then you can go to your TEM and then to think about the analysis. It's the analysis in TEM can be grouped into large 2 groups. Like this is imaging, diffraction, and spectroscopy. By using imaging, either coherent or incoherent, you can study about your specimen in the real space. By using, for example, conventional imaging, you see some precipitates or grain boundaries, and by using high resolution TEM, you can see some defects in your system. In this case, these are the vacancy layers. In diffraction, you switch your system to the reciprocal space, and then you can study about the crystal structure. You can extract here some lattice parameters. You can also, if your object's very small, you can use nanobeam electron diffraction. So you can focus your beam on up to several nanometers and then study. And then with convergent electron beam diffraction, you can also study many important properties like space groups and also in other properties. The spectroscopy here is divided into EDX. This is energy dispersive X-ray analysis. It's also a very famous analysis, and it's used in scanning electron microscopy. Here, by using the X-rays which are coming from the surface of the specimen due to the electron beam and specimen interaction, you can study the composition of your sample, composition of your precipitates. And here, this is the second analysis. This is called EELS. This is electron energy loss spectroscopy. Here you can study even your electronic structure. So by using the high resolution EELS, you can study band gap. So you can extract some optical properties from that. Also, you can study by using specific absorptions edges which are specific to the elements. You can study the chemical composition of your specimen. So these are both complementary method in the sense of composition, but from EELS you can study more. You can extract more information like band gap, surface plasmons, composition. Also oxidation states. This is very famous technique to distinguish between oxidation states in the material. So now to some basics of the imaging technique. So if you talk about HRTM imaging, we talk about electron beam, which is parallel. So the condenser system, it makes parallel, and then it illuminates the specimen. Should I wait? Or? Have power shutdown. But okay, so we create like electron beam, like parallel electron beam, and we illuminate our TM specimen. So we illuminate this irradiate with coherent electron beam with diameter of this larger than the diameter of the atoms. And the quality of our image, this is strongly depends on the so-called contrast transfer function. This is the property of the microscope, and this is the CTF, which you can calculate by using simulations software. So as we know that the resolution of our system, this is the properties of a lens system like CS and wavelength, and the CTF contrast transfer function for HRTM that gives the phase change of diffracted beams with respect to the direct beam, and only at the specific defocus, so-called Scherzer defocus, you can get the atomic columns resolved. So this is like for coherent imaging, this is like minus 1.2 CS lambda square root of this. In another case, you need to make a simulation. Here you have a HRTM image of very complex substances like lanthanum, zirconium, lithium, aluminum, and oxygen. Here you can get a nice image like a flowers. There's a central atoms and some flowers here. And if you do the image simulation, you can adjust it to the crystal structure, which are very complex, as you can see here. So for HRTM image, this is not the direct image because you have different focuses. You can focus your image and get lattice plane at a different focus value. The focus value only at this the focus value the image will the dark areas will correspond to the atomic areas, and the bright not. In other cases, you need the image simulation. So there is another method, so-called scanning transmission electron microscopy. Here, instead of using parallel electron beam, here we use focused electron beam, similar to the scanning electron microscope. Here you can see you can go up and down. Here they also scan through the sample. And what happens here? Your electrons can be scattered at different angles and can be collected by different detectors. One detector is called high angle analog dark field. And now this is analog dark field detector, and this is two bright field detectors. Here bright field, and this is analog bright field. With this detector, with bright field detector, you get the images comparable to HRTM images here. So, and if you collect the electrons scattered to very high angles, then the signal in such images, it will be proportional to the Z alpha, and this alpha can be between 1.6 and 2. Let's say we take as 2. The main point here that the intensity, they are proportional to the Z, and Z, this is the atomic number. So in such HADF images, we can directly distinguish between columns with a higher Z and the lower Z. So if we look to the germanium telluride in this case, so the atomic number of germanium is 32, of tellurium 55, and so we have here bright atomic columns coming from tellurium, and these atomic columns which comes from germanium. And if you don't believe to this technique HIDF, you can make a simulation for quantitative image interpretation, and you can see also nicely that these intensities, higher, brighter dots, they are tellurium, like here, because you have a structure model, you can compare it in the simulation, and then the less bright dots, these are germanium. So another signals, they contains also some signal which belongs to the HADF, and some which can be considered like coherent scattering. Now we also consider also one technique. This is imaging technique, and this is so-called electron tomography. As I said before, one limitation in TEM, we study always 2D projections of 3D samples, but it's possible also to reconstruct the 3D of your sample. In this case, what do you need? You need to tilt your samples to different angles and collect many images and then reconstruct them. So this is the image which is acquired at different angles here, and then it's reconstructed to the 3D image. Here, this is how does it look like. Here, this is the image. It shows you the nanoparticles embedded to the to amorphous matrix. You see here large fraction and small fraction, and the interest here is how they are distributed in the sample. Maybe a larger fraction can go to the surface, or it can stay in the bulk, or it can be a mixture of this. So after the 3D reconstruction, like here, you can nicely see that a large fraction is sitting on the surface of your specimen. So it was directly deposited on the carbon grid, on the grid covered by carbon. So there was no preparation in this case, only the image in tilting, and you can again hear that a larger fraction it sits on one surface of the sample. And so if you have such 3D image, you can also proceed with quantitative analysis of your images, like you can calculate the sizes and distribution in different places, and also the distances in between. So now a few words about image simulation. So we need this, as you have seen in the case of HRTM imaging, to understand the structure, because the image formation in the case of HRTM it involves like complex physical processes, and there are models which describe such processes, and they are like electron scattering diffractions. They are embedded in the image simulation packages, and they help us to understand the image you have seen experimentally acquired. So the main objectives of the simulation, this is the understanding what you see in your images, and also it helps understand the detail structure of your image, and also the improvement. Also, image simulation may help to understand how the image is formed and generate intuition on ways to improve the image and instrumentation. So these are very nice tool to estimate. For example, if you have such HRTM image, you make the simulation in your package, and then you can see at which defocus you get really atomic columns and at which not. So There are different approaches how to make image simulation. One is based on block wave. This is time consuming and very accurate, but very simple and fast, but also accurate. It's based on the multi-slice simulation. So how it's done, your sample is of specimen. It's like sliced into thin slices, and then the image divided into many slices, and then beam like alternatively transmit and propagate through these slices, and then it calculates your image. So it works very nice for the perfect crystals, for defects, and also it can be used for HADF imaging. So for image simulations, what you need to know about specimen parameters. You need also to know instrumentation parameters like defocus, CS, objective aperture. Also sampling size is also important. Scanning increment, and also the thickness of your specimen, just to adjust the number of slices in your simulations. So I think I can show you if it's work how so some simulations. So I have it on my computer. How it's work. I think it will be very fast if I get the internet connection. So now. So because I need to connect to my computer, since I don't have this program. Yeah, it's connected. So can I get the screen? My screen on the. Or I should close the this maybe, because it's not in the PowerPoint. defects. Yeah.
So if no questions, then just we will wind up today's session. So let's thank speaker again for completing this session. So thankful. Yeah. So we will start with our day 3 session tomorrow onwards. So we will have initially, I think day 3 we have whole lecture. Then day 4 again we have a tutorial along with hands-on session. Huh? So we'll discuss little bit about the experimental facilities which we have here, and then we'll show you the sputter unit which we have here, so you can have a feeling. Okay. So okay. Thank you. Thank you.